Let's get started. Good afternoon. I'm Dinesh Nurture from Computer Science and ECE. It's really an honor for me to welcome our speaker for the MRC colloquium, Jie Tan from Google DeepMind. Till 6 months ago, it was Google Brain. So it's currently Google DeepMind. I've known Jie Tan for a long time. He got his PhD with Karen Liu at Georgia Tech and has been at Google for, I think, for a long time.
Almost 8 years.
8 years. He's leading a very large group, at least it should be called Google Brain in Mountain View, dealing with a lot of robotics and machine learning. And of course, nowadays everybody's talking into what is called the foundation models. You know, what can foundation model do for everybody else besides, cheating in exam for ChatGPT here. So just to let you know, Jie Tan has done a lot of work in simulation, robotics, and learning, published a lot of great papers. And it just came from Atlanta, where he was program chair for one of the biggest conference called Coral. Some of us were there. Coral stands for Conference Robots Learning, which are 1,000 people. So this whole area of robotics and learning is exploding, and Jie Tan is one of the leaders who organized the Coral. So we're really fortunate Jie is here today and is going to tell us about robot foundation model training robots with internet scale data. Welcome, Jie.
Thanks for the introduction, Dinesh. Very nice words about me. Thank you. It's a great pleasure to be here today to share some of the recent projects we did at Google DeepMind. It's about robot foundation models, how we can leverage internet scale data to train our robots. So when we talk about robotics, this is often the mental image people have, right? These are the big, heavy machines. They are constrained in factory or lab environments. They are programmed to do one thing really well, precisely and repeatedly. These robots are useful, for example, in factory assembly lines, but these are very different from the robotics future we envision at Google DeepMind. Instead, we believe that robots is going to enter people's daily life. They are going to interact intimately with human beings. This means that these robots need to handle uncertainty, unstructured human environment, and they should have a very high standard for safety. This means that the traditional way of program robots might not be enough, because now you need to write a million if-else to catch all the corner cases these robots can encounter in the real world. So the robots really need to learn by themselves, very similar to how we humans learn to survive this complex and ever-changing world. So at Google DeepMind, our vision is to leverage machine learning techniques to build embodied AI responsibly to benefit people in the physical world. Since the founding of the team about 8 years ago, we have developed a lot of machine learning techniques, such as deep reinforcement learning, imitation learning, foundation models, to solve a large variety of problems in robotics, such as pick and place, dexterous in-hand manipulations, leverage foundation models to plan long horizon tasks, navigation in human-centered environments, dynamic and agile locomotion for quadruped robots. So the reason that we choose machine learning techniques or data-driven approach, because we believe this is one way to transform very difficult hard robotics problem to scalable data problems. And Google has a lot of expertise in handling large-scale data. Data is really powerful. Collectively, we human has produced a huge amount of data, like the text and images, and dumped them on the internet. In the last few years, we also have developed expressive architectures such as transformers that can absorb a huge amount of data. And these models are really big, right? Hundreds of billions of parameters. As we scale up the model size, the amount of data we can absorb also scale up. So now, originally, if you have only billions of parameters, you can only do language tasks. But now with hundreds of billion parameters, you can do all sorts of things: common sense reasoning, writing code, doing math, understanding semantics of the world, and so on and so forth. For example, you can carry out a very natural conversation with a large language model on a very specialized topic. you can ask it to do math. Actually, my 10-year-old at home often uses ChatGPT to learn math and physics. But on the flip side, it's also a powerful tool to cheat in his homeworks. We also have another type of foundation model called generative models. They can generate realistic images or videos from text. Just a few weeks ago, there's a very famous Chinese movie director who directed Wandering Earth came to Silicon Valley. He is very stressed because he feels that in just a year or two, people are just pumping scripts, and on the other end, the movie will come out automatically. That is going to put him out of job. I think he is overly stressed. But it's a trend that you can see, right? And recently, we get access to these multimodal foundation models that can understand images very well. For example, you can ask the model, can I go down this street on a bicycle? Yes or no? Then the foundation model is going to reason step by step. Initially, it sees this big red sign, do not enter. So do not enter. The next is see this square sign right below it, except with a drawing of bicycles. Then it starts to perform this logical reasoning, do not enter except bicycles, and give you the conclusion, yes, you can go down this street. Now we have a lot of diverse data collected from the internet. We have these expressive and capable models. The question is how we can leverage them to build a robot foundation model that can absorb internet scale of data or robot data and enable generalization to new tasks and environments. To answer this question, I think there are two key questions we need to answer first. One is how can we use the existing foundation model to control robots? The foundation model output language. What robots need is motor torque. So there is a gap between there. Second is we know that training foundation model need a lot of data. Where does these robot data come from? So today I'm going to go through three of our recent works, SayCan, Robot Transformer 2, and ROSIE, to shed some light to the answers of these questions. Going back to the first question, how to use foundation model to control robots. So at Google DeepMind, we focus a lot on the robot brain. So we get a lot of inspiration from human brains. So human brains consist of many components. Two very important components are the cerebrum and cerebellum. The cerebrum basically do the cognitive reasoning, such as common sense, planning, memory, semantic understanding, and many other higher level functionalities. Once you have a plan, then the cerebellum is going to be responsible for motor control to execute that plan. So first of all, I'm going to talk about SayCan, which leverage the common sense in large language models for long horizon task reasoning. So that's like a cerebrum for the robot brain. And next, I'm going to talk about RT2. It's a vision language action model that is fine-tuned from a vision language model for low-level motor control. Okay, talking about SayCan. Do as I can, not as I say. Grounding language in robotic affordance. So if one day I can buy this robot at home, what do I want the robot to do? So on the right, you see we call it meta robot. It's from Everyday Robots. It's supposed to be a household robot that can do many tasks for you. So these are three examples I would love my robot to do. I spilled my drink, can you help? Or I just did some workout, can you bring me something to recover? Or I'm feeling really tired, can you make me a coffee? But where are we? Do we have these robots yet? Obviously not. So in the lab, we focus mostly on the short horizon tasks, such as a pick and place. So on the right, you see a typical setup we use at the Google DeepMind to train these robots. And it's in a very controlled lab environment. A lot of engineers and scientists are writing C++, Python to program these robots. Where we want it to be, we want long horizon tasks. Making a coffee often consists a dozen or even more short primitive actions. We want it to be in the wild. It should enter my home, do things in an unstructured environment. And any user should be able to use natural language to communicate with these robots. So we find that language is the key here. A large language model provides you capabilities to make progress in these three horizons. Can we just apply the large language model to robots directly? What's the problem? So here, I spilled my drink, can you help? They will ask different language models. GPT-3 is going to say, you could try using a vacuum cleaner. That makes sense. Lambda say, do you want me to find a cleaner? Flan, which is another language model, said, I'm sorry, I didn't mean to spill it. It has some personalities. But the problem is, our robots can only do a handful of tasks, right? And we really need this long horizon task to be broken down into actionable steps, smaller steps. But the large language model does not know what kind of thing robots can do. It is not trained for it. In all the training data, it's a text and image on the internet, so it has no idea. In other words, we need to ground these language models based on robots' capabilities, or we need these language models to speak robot language. How can we do that? If you have played with large language models, you know that one way is called prompt engineering or in-context learning. So you can provide the large language model with many of these examples. Just take the first one as an example. How would you move the coffee to the counter? Then you provide answer. First step, find the coffee cup. Second step, pick up the coffee cup. Third, go to counter. 4, put down the coffee cup. 5, done. You provide many of these examples, and you would expect that the language model is going to give you responses in similar patterns. This is during the test time. You can ask, how would you put an apple on the table? But here is the key. If you let the language model to fill in the blanks, it's going to fill it in any way possible that you cannot imagine. So you need to ground it. Instead of let it do filling the blank problem, you should let it do multiple choices. You can list all the capabilities the robot can do, then use a scoring model of these foundation models to score them. For example, if you look at all these scores, the highest is -4. Pick up the apple. Right? These are all the things that the robot can do. And to put an apple on the table, pick up the apple is a reasonable first step. That makes sense. Then after you do this step, you can iteratively query the large language model in a similar way until you accomplish the entire task. So what's the problem? The problem is large language models, even though it can pick all these different skills you already have on the robot, it is not grounded in the real world. They don't know what's actually possible given robot's current state. For example, the robot is trying to clean your toilet in your bathroom. The first step of put an apple on the table definitely is not pick up an apple. Facing a toilet, it's very unlikely there's an apple there, right? The first step is probably you should find an apple. This means that we need to ground the large language model in robotics affordance. Yes?
Just a quick question in the previous slide. So, what is the most intuitive way, at least here, how the scores are decided?
How these scores are decided. So many of the large language models, they provide you a scoring function. So you can call that API, say that here is a context, here is I want to score different options. Then they can provide score directly. Okay, let's continue. So what is a robot affordance? It is the action possibility offered to a robot by its environment. For example, on the left image or the animation, you see the robot's observations. These are the camera input to the robot. On the right is the action possibility, how likely these actions is going to succeed on this state. If the robot is seeing a Coke, so all these bars on the right about picking up a Coke, finding a Coke, all these will shoot up. How can we get these robot affordance? At the time when we published the paper, we are using reinforcement learning to train these primitive actions, like pick up an apple or go to a certain place. And in reinforcement learning, there is this very important concept called value function. Right? That's a mapping between your current state and action to a value. So that's exactly robot affordance. Given the current state, you want to know what is a success rate or possibility of a certain action. So they are encoded in value functions. Lately, I don't think it's necessary to query value function or use reinforcement learning here. You can just ask a vision language model. You say, this is what I see. What's a likely action that can succeed this task? Then vision language model probably give you a reasonable answer. Okay, so SayCan basically is the idea that can combine the Say part from the large language model and the Can part based on the affordance models. So even though the language model said that you should pick up an apple, the affordance model said differently. So this is a typical, or the observation robot sees at that time. So it's middle of nowhere. There's no way it can pick up an apple. So affordance model is going to give a different type of rank, different scores based on where it is. Combining the scores, finding the apple is the most reasonable choice. Then you can do this iteratively until you reach the end of the task. Okay, let's take a look at some examples. So the user said that I spilled my Coke on the table. How would you throw it away and bring me something to help cleaning? Then the robot starts to query the language model and the affordance model. The first step, most reasonable thing, is to find the Coke can. And the second step is to pick up the Coke can. After it's successfully doing that, it's going to go to the trash can. Put down the Coke can. Remember that there are the second half of this query. It's find me something to clean it up. So it go and find a sponge. Pick up the sponge. Go back to the table. And put down the sponge. At that time, the robot is not equipped with a action primitive to mop the table, so it actually leaves that final task to the humans. But as soon as you have new primitives, you can easily add it to it. Then the language model is going to plan for you according to your existing primitives. There are tons of tasks that you can maybe watch offline. I'm going to skip many of these videos for the sake of time. So we have done comprehensive quantitative evaluations. Overall, we have evaluated over 100 instructions. Many of these are long horizon instructions that involve over 10 navigation and manipulation skills in a row. We achieved a 70% of planning success rate and a 61 execution success rate. Overall, if you multiply them together, the success rate is about 40-50%, not particularly high. But without the grounding, we can only achieve half of that performance. So some takeaways for this project. So large language model has captured a lot of common sense from the internet scale of text data. So it knows how to decompose a long horizon complex task into smaller steps. At the same time, affordance model tells what's possible for the robot to do in the current state. SayCan combines large language model and affordance model to ground the LLM based on robots' capabilities and what the environment offers. So there are a couple of limitations of this work. First, the planning success rate is not particularly high. It's only 70%. And the low-level skill is still the bottleneck. So I'm going to talk a little bit about the planning success rate here. So after the SayCan paper was published, we have a couple of follow-up papers to improve the planning success rate. One technique is called chain of thought prompting. I'm not going to dive into the details, but I just want to give you one example to give you some flavor how it looks like. If the human says, "How would you bring me a fruit that is not an apple?" If you just apply SayCan, it will just see the apple and bring you the apple. Totally ignore that not. But if you prompt it in a way that enables it to reason step by step, that's called chain of thought prompting. It will output some explanation first. It will say, oh, the user has requested me to bring a fruit that is not an apple. Banana is a fruit that is not an apple, so let me bring the user a banana. Then come up with the steps to bring you the banana. Just prompting it in the correct way is going to significantly improve the planning success rate. In addition to that, there's a couple of other papers, I'm not going to dive into details, that significantly improve the planning success rate. So far, we're not very concerned about planning. I want to highlight or emphasize one trend that we observed in the last year or so. That is, even if you do nothing, okay, let me roll back a little bit. So we start from the flat model, that is the blue dots here, that is underlying language model. Later, we swap it out and use the palm model without doing anything else, just swapping the underlying model, which is now more powerful. Our planning success rate increased significantly without us doing anything smart. That means that we're basically riding the wave of these large language models. Anytime they get progress, we get progress automatically. So one analogy is that you have a neighbor or neighboring research field. They are making rapid progress, and there's tons of money, thrown towards that field. So don't feel jealous and don't get scared. I think it's a best chance that you can ride the wave and make progress with this neighboring field. So the second limitation is low-level skill is still the bottleneck. These low-level skills are like manipulation, object navigation, and so on and so forth. We only have 60-ish success rate, so it's still the bottleneck. But this is also a good transition to talk about the second project. So we have already talked about SayCan, which is like a cerebrum of the robot brain. And the RT2 is to execute these low-level skills. As I have mentioned, it fine-tuned a vision language model for motor control. RT2, or Robot Transformer 2, is a vision language action model that can transfer web knowledge to robotics control.
Is this public or this is?
Oh, RT2 is public in Coral, just a few days ago.
Okay, thank you.
Yeah. So let's define a low-level control because it might mean very different things based on people's background. So here, low-level control means it's a mapping from instruction, like a natural language instruction, clean the table, and the robot's observation, especially from camera sensors, to the robot actions. What is vision language models? These are relatively new, which becomes really popular in this year and last year. The input of vision language model is the text and image. The text is usually a question about the image. Then the output of this vision language model is the answer of the image or of the question. I'm not going to dive into details of the architecture choice of different vision language models, but you can think of it as just a large transformer that absorbs a lot of web data. And partly is a model developed by Google DeepMind, and we use it extensively for robotics control. Other famous vision language model include like GPT-4V, which became available last month. So these vision language models encompass both the visual and semantic understanding of the world, given how much data it is trained on. And these are exactly what we need in robotics, right? Robots have a lot of visual inputs. It needs to understand the semantics of the world in order to make these decisions. The question is, how can we leverage all these knowledge captured in the vision language models? Let's going back to the low-level policy. You will notice that the input to the low-level policy happen to be the same as the input of the vision language models, the text or the instruction and observations. How about we just replace the low-level model with a pre-trained vision language model, like this? What's the problem? The problem is they output very different output. One is language to explain the questions about image. The other is the motor torque or any robot action you choose to use. In this particular example, but it can also generalize to other robots, here is the action space of the robot. It has 8 numbers. The first one is a binary decision, whether you want to terminate the current episode based on whether the task has accomplished or failed. Then you have 6 numbers about the delta of the pose of the end effector. And finally, you have 1 variable controlling the gripper. How can we make it as a language so that vision language model can output? Very easy. We make it a string. So more concretely, what we did is we discretize each of these numbers into 256 bins. Then we restrict the vocabulary of vision language model's output to integers ranging from 1 to 256. Then that aligns the vision language model's output and the robot's action space. This gives us the vision language action model. How do we train it? We start with some model backbone like PaLi or PaLM-E. So these are the architecture that we developed at Google. These are very big models. So the number in the parentheses is how large the model is. 5B is 5 billion, and the 12B is 12 billion parameters. Then we pre-train these models using web data. These web data are usually collected from the internet. They consist of an image, a question, and an example answer. So usually these are also called a VQA, Visual Q&A web data set. So we trained with a lot of these web data. Then we collect the robot data as well. So we have collected the teleoperation data or human demonstration data for the robot manipulation tasks. We have collected these data over 17 months on 13 robots in parallel. So it's a decent amount of data. Then we fine-tune this model, which is pre-trained, to get our RT2 model. Here is one detail that's very important. We do not just fine-tune using the robot data. We fine-tune by mix the robot data with the web data together. We call this co-fine-tuning. I'm going to provide slightly more detailed analysis in later slides. So let's take a look at some examples. Move banana to the water bottle. So the robot understands what's banana, what's water bottle. Move banana to 3. So it can recognize symbols that is handwritten on a piece of paper. Put strawberry into the correct bowl. So it needs a little bit of reasoning to understand I'm doing strawberry and which bowl is a matching bowl, then put it there. Move soccer ball to basketball. So it recognizes different type of balls. Move Coke can to Taylor Swift. The robot definitely is a fan of Taylor Swift. So after seeing all these photos and images on the internet, it can recognize people, especially celebrities. I'm going to skip all these different examples. There's a lot of them. But what we find is the robot actually, after the training, develop a lot of emergent skills. What do I mean by emergent skills? These are skills that is not shown up in the training data. Robot training data, right? They are in the web data. So for example, pick up the bag about to fall off the table. We never engineer a scenario there's a bag about to fall off the table, but it can just learn this automatically from the web data. Move banana to Germany. We never have data about flags. And pick land animals. Again, we don't have robot data that teach a robot this is animals live in the sea, these are on the land. So all these knowledge and information are captured in the internet scale of web data. So it sort of marries these internet scale of data in the web and also the robot pick and place data that we collected to do these language conditioned semantic manipulation. Here are more comprehensive quantitative evaluations. We find that RT2, which is based on pre-trained vision language models, significantly outperform all the baselines that is not leveraging vision language models, especially when the tasks require symbol understanding, reasoning, human recognition, and so on. One problem of the data-driven approach is that if your testing environment is very different from your training environment, then you have the out-of-distribution problem. So the performance deteriorate very rapidly.
I have a question regarding in the pre-training step, you have web data that are not necessarily from the same embodiment that you care about.
That's right.
How do you align the action space in that case?
Yeah, during pre-training, we don't have action at all. It's all about the vision Q&A. So output is also always language. During fine-tuning, we change the action space for the robot data to a smaller space described by integers. Then we mix them together. So there is no requirement to align the web data with your robot embodiment.
I see. So basically, you're using smaller number of data, a small amount of data for a specific alignment of this embodiment.
Yeah,
I see.
Exactly. So the big web data is for understanding semantics, understanding language, and there's small fine-tuning like robot data for physical manipulations. Okay.
It's like a kind of generalization over new scenarios.
That will give you the generalization over new scenario.
Yeah.
That's exactly what this slide is
Yeah.
for. Yes. Okay, so yeah, the performance is going to deteriorate if you encounter unseen objects, unseen backgrounds, unseen environments. Even though you have never seen these in robot data set, you probably see it on the web data, right? So this gives you a performance gain by a large margin comparing the RT2, which is based on vision language model, versus the baselines that is not based on vision language models. And finally, we did some ablation to understand the importance of code fine-tuning. Here we have three different approaches. One is you collect the robot data. You just learn this big model using the robot data from scratch. The second way is we pre-train with the web data, but we fine-tune only using the robot data. And third approach is we pre-train with the web data, and during fine-tuning, we mix the web data with the robot data, and we co-fine-tune with these data. The result is that the co-fine-tuning is necessary to achieve the best result. It's not surprising because of the catastrophic forgetting problem, right? If you just fine-tune with the robot data, it's going to forget all these web data it is trained on. But coming up with the right mixture, what is a portion of web data versus robot data is an art, requires a little bit of hand-tuning. The takeaways of this project include that Robot Transformer 2 is a vision language action model that is based on fine-tuning the vision language model for robot low-level control. And it improved generalization through language and semantic understanding using vision language models. The other thing is it enabled chain of thought reasoning. I mentioned chain of thought in the previous project. I didn't emphasize it here due to sake of time, but it's a very important capability for robots. Let me just give you one example. Here, you can have the instruction, move the green objects together. So chain of thought is going to divide this task into multiple steps. The can is green. The bag of chip is green. Moving them together means move the can to the bag of chip. So this chain of thought will enable the robot to reason more long horizon and complex tasks, then achieve it. Some limitation of this project. One is we see very limited generalization for physical skills. All the robot training data is pick and place, and it does not generalize to open the drawer or more dexterous manipulations. This is also not surprising given all the physical information, physical interaction is provided by the robot data. It's not in the web data for vision language models. The second is these models are super big, billions or tens of billions of parameters. It's very difficult to perform fast inference. There's no way that we can host this model in a local GPU and run it on board. So we always host these models in the cloud, use multiple TPUs to perform inference and send the commands back to the robot. That means that the control rate is about 2 to 3 hertz. It's okay for these semi-static operations for the manipulation tasks, but if you are thinking about locomotion or self-driving with very high safety requirements, this is not going to work. So we have some ideas how to improve the control frequencies, such as how to distill a big model into a smaller model while retain most of the capabilities, then run this smaller model on board. I also had a discussion over lunch with Bahar. I think she is thinking about how to develop a system or the computer architecture that can perform more efficient inference on board. Okay, let's go back to so I think we already understand how we can use these foundation models for robot control. Let's go to the second question. Where is the robot data from? So here are two axes. We care a lot about the quantity and the quality of the data. We can collect the robot data by what we did in RT2. We set up many robots in parallel, then we collect them day and night. These are high quality data because these are real world data on real robots. So it has the right action space and so on. But it's very hard to scale it up. So the quantity is very low. The other way is we can collaborate with the entire research community. and try to pull data together from different institutions. So very recently, Google DeepMind has released a paper called RTX. So we collaborate with over 30 research institutes. Every one of them contribute data, we put them together, train a big model, and then they can evaluate this model on their own embodiments. The data is more heterogeneous, so it's hard to use, but then we get more data. The third way is fully leverage the data on the internet, such as YouTube data. For example, on YouTube, there are all these data. I want to show my house. So I take a GoPro and show here is a living room, here is the bedroom, and so on. Or someone just have the virtual tour of them. They have a GoPro and walk on the Paris and explain it. All these data are valuable navigation data, so we can leverage them. And finally, we have physics simulations. Simulations are very fast, can run in parallel, so you can collect almost infinite amount of data in simulations. But we also know that there's a sim-to-real gap. So these are relatively low quality data. Even if you train a good policy using simulation data, there's no guarantee it's going to work on real robots. So there is this trade-off between quality and quantity. The question is there anything there at that corner give you good quality by large amount? So that's the last project I'm going to talk about, ROSIE, how to use AI-generated content for data augmentation. Scaling robots learning with semantically imagined experience. So we had a lot of progress in the last year or two in text-to-image generative models. So here is ImageN. You basically type in text, it's going to generate creative and realistic images for you. We can use the same technique in ROSIE. So here is what the robot is actually collecting data from. It's in a typical micro kitchen at Google. Then it can imagine or hallucinate I'm in different place. What if I'm at people's home or in office environment with different furniture, with different lighting conditions? Right? It's all in the imagination. So we don't need to physically move the robot there to collect the data. Back to reality. It realized that it's still picking up a Coke can in micro kitchen. Very sad. So we can divide the ROSIE into 4 different components. I just briefly dive into each of these so you get a sense how the method works. The first step is we have a large language model to propose where to augment. Okay, you can say that how I want to change the scene, then a large language model is going to give you some prompts that you can leverage in later stages. The second stage is doing segmentation to figure out which part you want to replace with imagination. And the third part is to use the ImageN. It's a diffusion model to in-paint that mask region. And finally, you mix all these data together with the real data and train the policy. Okay, in the first step, you have the source task. That's the actual task the robot is collecting data, such as place Coke can into the top drawer. Then you have a target task. You can say that I want the robot to place Coke in a cluttered top drawer. Okay, the key is cluttered. Then with the right prompting, it's going to output these different prompts. At first, it's going to tell you which region the message should change. For example, the open the drawer is where ImageN should change. And it also specifies pass-through objects. I don't want to change the robot arm. I don't want to change the gripper. And then it also provides you the in-painting prompt. Add a toy block in the drawer. The block has different colors. That's its own understanding of clutter or clutter. So given this information, we use an open vocabulary detection and segmentation model to identify where to alter the image and where we should not touch the image. Then we use ImageN and use the text prompt given by the first step to add additional blocks or the Coke cans into the top drawer. Then we collect these data, mix it with the original data in the 1-to-1 ratio, and then use this augmented data set to train the robot. A few more examples. In addition to just change the entire background, you can also change what the robot is trying to manipulate. From a drawer with a bag of chip, you can change whatever you like. and after the robot grasps the object, you can also change the object in manipulation and into like different type of cloths with different textures, even different physical properties. Just to look at how realistic they are. They have wrinkles and so on. Even though there's no simulation, physical simulation, all the generated image looks so realistic. Okay, now we are going to show the entire system, how ROSIE is going to work end-to-end in practice by rolling out policies that is learned on this augmented data set. Note that these scenarios, they only think through the diffusion model. The robot has not collected data in these scenarios. So one is to put things or manipulate things in kitchen sink. The robot has never seen kitchen sink. It only see a drawer that is open. But we replace that drawer with all kinds of different kitchen sinks. Then on the right, after it's trained on the mixture of these data, it can successfully perform manipulation tasks in kitchen sinks. And you can compare that with baselines. That is trained without data augmentation. So on the left is RT1. It's the previous paper we have, a good manipulation policy, because it has never seen kitchen sinks. It failed to manipulate things in front of the kitchen sink. But on the right is RT1 with ROSIE. So it's the same policy, but just with a different augmented data set. And the success rate is significantly improved with the ROSIE data augmentation. We have done more comprehensive evaluations. If you compare no augmentation with ROSIE, you can see a huge gain in success rate for those unseen environment and unseen backgrounds. To sum up, so data augmentation via off-the-shelf text-guided image generation is a very important tool. It has significantly improved data diversity and generalization of manipulation policies. There are a few limitations and that we want to address in future work. One is we only augment appearance. Right? We only have these text-to-image models. It does not augment physical interactions. Second, we are not enforcing temporal coherency as we're collecting these data. From that kitchen sink example, you can see that it flips like every frame to change to a different kitchen sink. So there is no temporal coherency. But it seems that it's not a big deal. We don't see a lot of impact or negative impact in the final performance of the downstream task. But we can always use the state-of-art video generation tools. Video generation is not as good as image generation at the moment. It's also more costly, but it's a trade-off between temporal coherency versus computation speed. Finally, it's very computationally expensive. You need a very beefy GPU, a couple of seconds to generate just one image. But the good thing is it's very scalable. You can run it in thousands of machines, at least at Google, to generate many things in parallel. So it's scalable, even though it's expensive at the moment. Okay, just want to quickly summarize today's talk. So I have dived into why foundation model is so important for robotics. I think that it has solved or partially solved three fundamental problems in robotics. We often complain that robots don't have common sense, but now large language model has a lot of common sense, and we can leverage it to give robots common sense. Another thing is generalization. As you have seen in the RT2 example, the robot can understand the language when you put it differently or see different scenarios. It can generalize to these unseen environments. And finally, it enables interaction with human using natural language. I think it's a big deal. I also talk about how can we use foundation models to control robots. SayCan is like the high-level reasoning cognitive cerebrum that grounds large language model for long horizon task planning problems. Once you have a plan, you can use RT2 to do low-level control, and RT2 fine-tune the vision language model to give us a vision language action model that can generalize to different manipulation tasks. And finally, where is the robot data from? So we should use any data possible, no matter it's just we set up robots to collect data in the real world, or we collaborate with different university and institute to pull data together, or use YouTube, use data from the internet or in a simulation. But another, I think a newly emerged technique is use these AI generative models to generate data for robotics. Looking forward, I think to train a really powerful robot foundation models, the remaining challenge is still on the data side. So how much data do we need? What kind of data do we need? How diverse these data need to be is still an unanswered question. We just barely scratch the surface, make a little bit of progress, but data, I think in the next few years will be a big problem and will be the bottleneck. So in the last minute or so, I want to zoom out and talk about the big picture. A few years ago, when people say we want to use large data and train an end-to-end system for robotics, I don't believe it at all. Right? Once you have a large model, you need like exponentially more data to train it. And how can we get so much data on robots? It's a chicken and egg problem. If you don't have the data, you don't have the performance, so you cannot sell these robots to everybody. If not everybody have the robots, how can you collect all these data in scale? So it's not solved. It's not solvable. But after 2 years, I'm now a believer of using data-driven approach. The reason is because I no longer believe that we need a huge amount of robot data. So what has changed is these internet scale data, these foundation models that captured the knowledge in these data in the internet scale, and we can use pre-training to form the basis for robot policies. I believe these data will be like 99.98% of all the data you will need, and we have that. Next, we are going to collect a reasonable amount of robot data. These data will from different robot embodiments. They are from like a different task. It could be a spot walking the campus here. It could be a manipulator collecting data in Google Office. But the key idea is that we are going to pull these data together as a community, so we have the diversity and the quantity of robot data. You might be curious. So these data are so different. Some are like a quadruped data, some are the real robot data, some are manipulation. How could we train one model that can do all of them? But remember, the model we are training is very big. Right? A few years ago, I don't know how we can train one model that can do math, can do physics, can do language, all of them together. But with a big model, we see that these models can build different pathways for different specialization to master different skills. Even better, these foundation models give us the opportunity for in-context learning. Right? So at the end of the day, you want to provide some examples to these robots. Here is how I want the task to be achieved. Or if you want something really high performance, you can provide a few shots of the demonstration data, use it as a prompt, like you prompt the large language models. So the robot can perform tasks in high performance or according to your preference. Once everything is trained, you should be able to deploy these on different type of robots in different environments to achieve very different tasks. And finally, I want to thank all my collaborators. So we are a very, very big team. We have 150 people in Google DeepMind Robotics. We are located in Mountain View, in New York, in London, in many different places. I really thank them because they are the people who do the hard work to make these papers happen. I'm just a lucky one who stand here and tell you the stories. And finally, I want to thank you for your attention.
There also for there's a big audience on streaming, do it. So we can take the question from the audience. Maybe I will start. You really believe large language models have the common sense?
I do. Yes. I don't know what's the mechanism behind it, but from the behavior, from the appearance, it seems to have common sense. And that's enough, maybe. Yeah. Maybe it's a different common sense how your brain works. At least, all the data points shows it seems to have some common sense about the world. At least it understands the world, somewhat similar to humans' knowledge how the world works.
Question in the room, Livia.
Thank you. That was very interesting. So, in the case of for data augmentation, is the data augmentation done on the basis of what the robot sees at test time, or is data pre-generated augmented?
It's pre-generated. So the robot, we don't use
Can you just repeat the question?
Yeah, the question is, good point. Yeah, the question is for the data augmentation, are these generate data based on the test time scenario, or it's just generated prior to that, so it's independent to the test time? So it's independent of the test time.
So in that case, isn't that another hyperparameter to solve, because we need to figure out what variations of the data to generate, how much to generate?
Yes, that's another thing. But at least you have the tool to generate many, many data in large scale, which this tool was not available to us just like 3 years ago. Yes, but you are right. So what data to generate to ensure the diversity of the data is a question.
James?
So I have a somewhat similar question, and also it's with ROSIE and RT2. So RT2 showed that with the internet data, you didn't necessarily need to augment your data set. Like the sync example that you had in ROSIE, the RT2 model should be able to complete that task because it knows what the sync is. So I guess my question is, what is the utility of ROSIE when RT2 can do it using the internet scale data?
This is a great question. The question is, RT2 should be able to generalize to different semantics and images. And RT2 is trying to do augmentation to improve the generalization of images and visual input. Why do we need ROSIE if RT2 can already solve it? Right? So the reason that you feel that way is because of the date of publication is reversed to the order I present the paper. So we did ROSIE first, then we do RT2. Yes, maybe nowadays ROSIE is not that important anymore, but I still think that in certain scenarios, in some like weird scenarios, maybe it is not covered by the internet scale data. You can still use AI to generate some data that fill in the gaps.
Soma?
So yeah, I have a question. Like I saw that you use large pre-training data to train the robots, right? So I was just wondering, like in this data set, do you face while training the robots some issues related to spurious correlations, or like we know, right, like the diffusion model suffers from lack of image compositionality. So after you train the robots, have you faced like there are some problems in that domain after you train the robots?
So the question is, we know that there are some difficulties when you generate images like a compositionality. So do I experience those?
Yeah, like
right.
Yeah, some issues like in real life after training the robot. Do you see those things?
Yeah. So we do see a lot of issues. So it's not like these images are very nice. They are a little bit cherry picked as well. So the difficulty that we see is the segmentation actually sometimes fails. So it's not all that clean segmentation where you want to augment. Then once you augment, yes, some of the problems show up as well. So it's not that great yet, but it's still, again, as I said, many of these artifacts does not impact the downstream tasks. Like temporal coherency is a problem that we see as well, but it does not impact the performance of the manipulation.
So let's mix a question from the audience.
Yes.
So a lot of professors are asking, how can university with limited resources can develop and use this model? Can we get RT2 with ROSIE? Everybody wants it, right? That's the biggest, most frequently asked question.
I think for diffusion models, it's possible. So training diffusion models or fine-tuning diffusion model is not that costly. And for large language models, it's harder. But there's also like open source, large language models from Meta and from other places you can play with. I hope that Google will eventually open source some like checkpoints so that you can fine-tune as well. I don't have the timeline in my mind. I cannot speak for Google DeepMind about all these milestones. The other way is that it's quite successful in the past. Is the university and us can collaborate. We pull data together. Then we can share a checkpoints by using all these data, trained by all these data. Then each individual labs can run these checkpoints on their embodiment and evaluate them. So in this way that we have more data and we have more fair evaluation. It's not like Google, in the lab we crunch out all these numbers, but all the university is trying to do the evaluation, then we put the number together.
Hi, Jie. Thanks for the great talk. One question is, you mentioned the challenge is, it just augments appearance and not probably considers interactions and action spaces there. So I'm kind of curious, like, what is the next step there? Like, one work is like from, I think, Tony and Chelsea from action chunking with transformers, essentially. Would that help? But in this case, also diffusion brings a challenge. Like, it's only continuous spaces where we can use it, but it's difficult to go for discontinuous spaces, which are often real world problems. So kind of curious about your takes on that.
Okay. The question is how we can go beyond just augmentation with images. You want more physical interaction and so on. So one way is how can we scale up data collection on robots. So Chelsea's and Tony's work on like Aloha basically significantly reduce the barrier of collecting puppeteering data. So that's definitely one way to do it. The second thing, as I mentioned, that we should collaborate and pull data together. The third thing I think is very promising is these video foundation models. It's not as good as image foundation or vision language models yet, but videos capture all these physical interactions, causalities and physics. So I believe that hopefully next year, when we have a big video foundation model, we learn a lot about the physical interactions, then we can bootstrap from that foundation model.
Just quick question. Thank you for the excellent talk. So when these actions are learned, do you also focus on like the confidence with which robots should take? Because you mentioned about safety, right? So like, is that connection has been made or yet needs to be done?
So the question is when we fine-tuning these foundation models, do we have a confidence measure? How confident you are about the output? So in these three talks, no, not yet. But there are other works, like you probably know that Alan's work. So Alan was a student researcher at Google DeepMind, so I work closely with him as well. So he recently have a paper about how we can keep a confidence level of certain decisions and then ask a human if it's uncertain about what to do. And it was actually the best student paper award in Coral. Just to get award yesterday, yes.
Question, go ahead.
Hello, thank you so much for your talk. I wanted to ask, SayCan is very good with long horizon planning, and it generally subtask the primary task into subtask. And suppose for some reason there were 5 subtasks that it was supposed to do, but it failed at the 3rd task. How are we dealing with that particular scenario? And one of the papers that I recently read, which was dealing about this particular problem statement, was it was using other language model like 3 or 2 language models, and it was going to and fro between those 2 particular language models to go again and ask, and then it will replan itself, and then will go to the original planning and it will plan it. But doing this requires a lot of computation resources. And first question is, do we have any other method to deal with such scenario? Second question, if the first one is what we are going with, do we have a method to optimize this large language use of large language models, multiple large language models that we are working with?
I see. So the question is, SayCan is basically an open loop controller. You plan the sequence and you just do it. What if you failed at the middle, right? And if you fail at the middle, there are some like a related work that use other language models to fix it. So it's very costly. I think Google DeepMind has a couple papers, like in the monologue, is to make the SayCan closed loop. So again, it's also using a different vision language model or another large language model to decide whether this task has been successful or not. So if it's not successful, then it replan or re-execute. It's a very common trend that people start to leverage vision language model and the large language model for all these different like success detection. Yes, it's very costly. We are mostly actually moved towards that direction. So we are also using multiple models to close the loop. In terms of the speed or the inference speed or the computation cost, yes, it's a big concern. So I think in the future we can develop a smaller, more specialized models. This is only for success detection. That is only for understanding human language and so on. Then in this way we can deploy it. Some of them in the cloud for big task planning. Some of these is deployed on board to do faster decision whether we want to continue or just replan. There is no conclusion yet. What's the best strategy? People are still exploring this space.
So let me take one question from online. So Jing asks, was the generated data evaluated good or bad for training? Could you share some experience for quality of generated data? The data you generate, is it good or bad for training? Did you use it for training basically?
So can I comment on
Quality of generated data.
quality of the generative data? So quality usually comes from two sources. One is realism, so that you train on these data, so there is no sim to real gap, right? Or the AI generate data real world gap. That's one thing. The second thing is the diversity of the data that really help you generalization. So far we have not derived the metrics, like quantitative metrics, to evaluate the quality of these data augmentations. But we do have some sense what are the important axes we should make progress.
Yeah, so how scalable these sort of systems are for out-of-domain generalization, or just to take a cue from the previous question, so how do we use LLMs to sort of mitigate this gap in this space? So any thoughts on that line?
Can you repeat the first part of the question?
Yeah, so I was asking how scalable these systems are for out-of-domain generalization cases, or have you did
How
any
scalable are these methods for out of OOD generation? The OOD is when you do the generation, but your training of your diffusion model is out of distribution, or you are doing OOD for the robot task. So these are two different OOD.
Yeah. So I'm thinking that if it could be like presented with a situation which it has not seen before, or something like that. So yeah, for different downstream tasks. So how does such system scale? Is any thoughts on that?
Yeah. So currently we use a lot of like automatically generated instructions to fill different part of the image. So currently it's more based on like either crowdsourced generation or a random generation of these augmentation instructions. I think there is definitely an area that you can do research. It's like active learning. You generate some data, but you still see some failures. You sort of know how you can generate more like auto-distribution data to address that less of coverage in certain areas. I think these are still the area for exploration. We have some ideas. We don't have papers on this yet.
So let me take an online question. Chatterjee, how can robots be designed to intuitively understand and address situations like incorrect route choice or drink spills?
How can
robots be designed to intuitively understand and address? No, this is common sense, right?
Yeah, this is the common sense. Large language model give you that common sense, right?
Proactive intervening without needing to be asked. So I guess that's what people are asking. You're convinced that this question: how can robot be designed to understand situations? So
I don't think robot need to be designed to understand it. Large language model need to understand it. That's a
will solve the problem.
Yeah.
RT2 will solve robots' problem. Hopefully.
Maybe RT5, RT6. I think RT2 is still have a lot of limitations and failures at the moment.
Okay.
So right now you are focusing on the task that the video and text information are somewhat enough. And fortunately, when we use large-scale web data, all such data like videos, text can be easily recorded. So I'm wondering if for some other tasks that might require something like touch, taste, smell, it's hard to easily record such data and store them on the web page, on the websites. I'm wondering, do you think the AM or LLM can still help for such tasks?
Yeah. So the question is, we know how internet contains the image data, video data, and text data.
Yeah.
But there's a lot of modality robots have, such as tactile sensing and other things cannot easily be uploaded to the internet or even be shared. So are these information important, and how we can train from these data?
And do you think the large video language model can still help with such tasks?
Okay, large language model can help with these tasks?
Yeah.
So, so the first question is, it's very difficult for other sensor modalities. I think it's relatively easy for audio, video, image, text. These are the, internet is full of these. Anything else, like physical interactions or, tactile sensing, these will not easily come into the internet. So this will be the same as we collect robot data. It's for physical interaction. So you are going to collect robot data for a certain sensor modality. Then you use these to fine-tune the vision language model pre-trained on the web data. The second question is whether large language model will help. Yes, it will help as long as you have a system to describe in language of these sensor modalities. For example, you have I don't know, tactile sensing, then you can describe it. Oh, I feel a strong push on my elbow. You describe that to a large language model. Then a language model with the context maybe say, oh, it's a very dangerous situation, I should shut down, or things like that. So there's already a lot of the papers that say, I have all these different modalities. I talked to Yannis this morning. He showed me one paper that I have all these modalities, and I can grab certain things from these modality, describe it in text, and ask a large language model, what should I do?
Thank you very much.
Yeah.
Go ahead, you have a question.
I was just wondering if you could think of any interpretable visualizations that can help explain the success that ROSIE has in decision making.
Do I have any visualization to explain the success of the ROSIE, right?
Mm-hmm.
I don't. I wish I have. That would make debugging and development much easier. But the thing is, it's so hard to interpret these foundation models, no matter it's a generative model or it's a language model. So maybe it could be a very good exploration area, because these are the things that we really need. Otherwise, it's a lot of trial and error, and training these models takes a long time. So each time you want to try one thing, it takes a long time. So there is more analysis tools that will definitely improve the iteration speed of these type of research.
Christian, right?
Yeah, so I have a question. So previously you mentioned there's a balance between the general data on the internet and the task-specific data you collected for robot. Has there been any efforts on how to find the balance, or any insights or tricks that you have done?
Yeah, so finding the balance is you should just add them together, right? You mix them with different proportions. Like exactly what is the proportion is a little bit of art. You play with it. So we don't have a general guideline to it. But if you have a too small portion of your robot data, then the robot data is not going to be enough, and vice versa. So we relies heavily on a little bit of fine-tuning. We have many different recipes to fine-tune these models and choose the best one.
So basically now it's mostly based on empirical.
It's based on empirical, but the key is you need both data sets there. So nowadays when we train large models, it's more than just the web data and manipulation data. We start to put in navigation data as well. We just hope that when we have a big enough, large capacity enough model, it can absorb these data and build the positive transfer among these data sets.
Thank you.
Let's take last one or two questions. Go ahead, James.
To build on that question, since the scale of the internet data and the robot data are such complete mismatches, how do you do anything to select specific parts of the internet data that you want to use when you're mixing them, or do you just take the next batch?
So currently we don't do active selecting like which batch of data, but once we're trying to do some idea of distillation to a smaller model so that you can run it in higher frequency on board, that is a necessary step.
Last question.
Can you comment on how easy it is to hack these models?
How easy it is to hack these models. So can you define hack?
Hack as in there will be terrorist attacks. These robots will be working in the house.
Mm-hmm.
So they can modify the data. So I'm not a computer science person.
Yeah.
I just have this concern.
I think from my personal experience playing with these models, it's relatively easy to hack these models. You just provide some examples that will guide the models to do bad things. So different companies have different strategies for it. For example, OpenAI has some safety filters. If the output is not safe to human beings, they are going to just filter it out and say we are not available at this time. Right? Google has similar strategies, but there's a lot of work going on safety and responsive AI to tackle this challenge. It's not easy. It's hard and important for just a chatbot already. You can imagine how important it is for robots, because you are going to interact with it every day, and it has a physical power to hurt humans. So that is a very important research area.
One
can I
very
ask-
last question.
Okay, so thanks. So as we know that generalization is a really big issue in the robot learning. As you talk like using large language model, because language itself encodes the knowledge about human word. It already can have some information about word language itself. And another way you use like training from YouTube video or in the wild data like online videos. Another way you did like data augmentation like ROSIE. So do you have any more like suggestion about how to make a robot can be more generalizable? As you show the video, like it's more like pick and up actions. Can we generalize to be more other actions like humans? And any suggestion about to make robot more generalizable, or have you like using some technique about like a meta learning something?
Usually, in high level, I think there are two ways to tackle the problem, and these two ways are not mutually exclusive, and they should be combined. One way is the data problem. Just collect the out of distribution data every time you encounter it. So collect as much data as possible, diverse data as possible. The second is you be smart for the structure of your model. So you leverage prior knowledge or existing structure or physical understanding of the things, so that you engineer a structure or architecture of your model that already captures the essence of the physical world. So I think these are the two high-level ideas, maybe too broad to be concrete, but overall I think all the methods can be fall into one of these.
Okay, let's thank the speaker.
Thank you very much.